So could you please tell us about who you are?
Yes, hello everyone. I'm Jim Hermanson. I'm a professor in the William E. Boeing Department of Aeronautics and Astronautics at the University of Washington. Before that, I was on the faculty of the Mechanical Engineering Department at Worcester Polytechnic Institute in Worcester, Massachusetts. And I also have 9 years of industry experience with United Technologies Corporation and Boeing Aerospace.
And why did you choose to become an aerospace engineer?
I love that question. And it's something I ask my students all the time. What motivated you to get into aerospace? And with me, it was the Apollo landings on the moon when I was a teenager. I saw that, and I'd been interested in science since grade school. And when I saw people going to the moon, I thought that is just so exciting. That's what I want to do. And so that prompted my interest in aerospace and has propelled, pun intended, me throughout my career so far.
Mhm. And your interests are based on combustion. So could you talk about why you chose to specialize in this area?
Actually, I like to think of myself as a rocket scientist. I tell my students half jokingly that, you can all be rocket scientists. Rocket science is actually, there are more difficult problems and more complicated machines than rockets. But rocket science is great. And so the research I've been doing and the work I've been doing has generally been focused on problems related to that. So going into space is complicated. You need structures and control systems and life support systems, propulsion, all kinds of things. It's the propulsion part I like the best, seeing rockets in action. So the work I've been doing has all been centered around problems related to rocket propulsion. So that might include combustion, as you mentioned. And I'm doing some further work in that now. And I did my PhD in turbulent reacting flow at Caltech. So combustion is part of it. High-speed flow, supersonic flow is required for rockets to work. That's another part of it. And heat transfer and propellant handling is another part of it. So I've been doing various parts of rocket-related things. So that's my interest in combustion. It goes beyond that. Combustion is vitally important for lots of other applications. We rely on it for transportation. We rely on it for energy, many industrial processes. And so I've been working in that as well. We're all interested in improving combustion efficiency, decreasing combustion emissions, alternative fuel utilization, lots of other practical problems.
Mm-hmm. And could you explain the problems that you're trying to alleviate with your work on compressible flow?
Compressible flow is part of, again, that's part of the rocket problem. Rockets wouldn't fly without supersonic flow at the exit. But then beyond that, I've also done work in supersonic flow. And there's a continuing interest in supersonic flow for high-speed propulsion and aircraft applications. Now there's an increasing focus on hypersonics, on hypersonic systems and aircraft. So I've been working in compressible flow, both in the sense of how does compressible flow impact mixing processes, and also I've been looking at how it affects fuel atomization and droplet behavior.
Mm-hmm.
Compressible flow is a broad field, and there are people that work in shock waves, and I've done some of that. There are people that are interested in skin friction, flow stability, drag on hypersonic flows, and other related problems.
Mm-hmm. And what is a two-phase flow, and how is it used in aerospace engineering?
Two-phase flow is anything where the substance changes from one phase to another. In the work I've been doing, that's mostly liquids to vapor and gases. For example, if you burn any liquid fuel, it has to be atomized. It has to turn into a vapor so that it can burn. So the combustion process relies on that atomization and vaporization process. I've also been working most recently a lot in cryogenic propellant handling. That's a big deal for space. Hydrogen and oxygen are among the most energetic rocket fuels. Rocket propellants, they're great. They have to be handled under cryogenic conditions. And how do you store, how do you handle, how do you transfer cryogenic fluids on orbit, for example? Lots of issues related to how does the cryogenic fluid condense, how does it vaporize, how does it boil, and how much mass is ejected and what sort of heat transfer you get. There are a lot of uncertainty. So that's motivated my work in multi-phase flow. That also includes, of course, solids and liquids to solids and freezing and melting and all that. I've done less of that. With me, it's mostly been liquids and vapors.
Mhm. And what are the differences between the distribution of droplets in subsonic and supersonic speeds?
The droplet problem is a comparatively narrow area in the supersonic flow research area. The entire problem is if you want to fly supersonically or hypersonically, you reach a point where the processes in the combustor are so fast that there's no time, that the flow inside the combustor can actually be supersonic. That's a supersonic combustion ramjet or scramjet. There's an increasing interest in using liquid fuels. You'd like to use normal jet fuel, for example, instead of liquid hydrogen. In that case, atomizing the fuel, turning the fuel into droplets and then vaporizing the droplets is very important to get the scramjet to work properly. And there's no time for this. So it has to happen very rapidly. The research I've been doing has been focusing on what happens to the droplets. That's kind of the end stage. They've already been atomized into droplets. How do the droplets behave in supersonic flow versus subsonic flow? Most of the work on droplets has been done on subsonic flow, which is also important. I've been focusing on what happens to droplets when the flow around them is supersonic, and you see different things than you do in subsonic flow.
Mhm.
It's fun research. It's all fun and intriguing research to do.
Mhm. And you also have an interest in astrobiology. So could you talk about some of your research in astrobiology?
My interest in astrobiology comes from a couple of things. First, I've been passionate about astronomy, going way back to grade school. And I'm an amateur astronomer and I enjoy that part of it. So I connected with the astrobiology department. Their interest, of course, is on life on other planets primarily, a heavy focus on Mars, for example, and elsewhere. My interest in working with them is from the thermodynamics point of view. Okay, what's the environment on Mars like? How much water is there? Where is it? Is it likely ice? Is it mixed with something else? Is it likely liquid? When is it liquid? Where might it be liquid? So I bring into the astrobiology discussions some of the engineering considerations. How much heat is there? How much light is there? How much water is there? That sort of thing. All of which they need for life.
Mhm. Well, what would you say has been your toughest accomplishment so far?
I think all of engineering is tough. I found that out when I was a undergraduate student. And I remember there was another person on our dorm room floor that came in. I was studying with another engineering student in my class. And this person said, "You guys just study all the time." And we said, "Yeah, and engineering is hard." So aerospace engineering is a demanding major. All of engineering is demanding, all of physical science. So getting degrees is challenging. Getting a graduate degree from a strong institution like Caltech, that was very challenging. A lot of work under very, very intense circumstances. That worked well. And then in academia too, getting through the academic system, getting promoted, moving up through the academic ranks, that's a challenge too. So all of those are accomplishments. Hard to say which is the toughest. Technically, research topics vary. There's kind of a challenge, kind of a balance here. You can do problems that are fairly direct in the sense the experiment will work. So we've done work in combustion, for example, lighting off a flame. Okay, the flame will work. Then the challenge is find something that's new. Okay, what's new in a turbulent diffusion flame that we can learn? Or you can do an experiment that's very difficult, and getting droplets to inject and behave in supersonic flow, that was a really difficult experiment to do. But when you get there, you've done something that no one else has done. So you get real novelty. So I'd say all of research is challenging. Getting the engineering training is challenging. Hard to point to any one thing, but they've all been worthwhile in balance.
Mhm. And what is a big milestone that you're looking forward to in your research?
Next up, I've been doing more work in cryogenic propellant handling. And so I'm in the process of generating some new programs in that area that can have a big effect. NASA is particularly interested in transferring propellants on orbit. And there's a lot that's not known about how these cryogenic propellants, oxygen, hydrogen and liquid methane, for example, how do they work? How does that transfer work under microgravity conditions where there's no gravity keeping the fluid where you think it should be? So you don't know where the liquid is. You don't know how it's interacting with the surfaces, which are complicated in nature. So looking forward to that, if our group can have an impact on propellant handling and boiling, that could have an impact on NASA space missions, deep space missions going forward. I think that would be really cool stuff to do. And we have connections with NASA and industry doing that. And yeah, that's exciting work.
Mhm. And to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
A lot of this advice everyone's heard, find good opportunities, apply for them, work hard, get good advice, find people that can support you, find mentors, that can help you along the way. I think the biggest thing is probably passion, really being excited about it and believing in it. And we all had that experience. We get it in high school, we get it in college, we certainly do in graduate school, where we wonder, why am I doing all this? This is so difficult. So many deadlines, so many projects, grades, things not working. How can I possibly get it all done? We do, and to remember why. So I think my biggest advice would be always remember the why. Have a passion for what drew you into aerospace, what excites you about it, and why are we doing this? So hold on to that passion. It's a great goal. And always take time to take a little break and remember why we're doing this. For example, when we're outside walking, an airplane flies over. And I remember once when I was an undergraduate in the midst of my junior or senior year, overwhelmed by everything, I was walking back to the dorm at night and I saw an airplane coming in on approach. And it came in on approach and it lit up and you could see the landing gear coming down. And I thought that was just really cool. I thought, yeah, that's what I want to do. But keep the passion, remember why you're doing it, work a lot with people who can help you and get mentors and work with your colleagues. And it's a great career. I really recommend it.
Mhm. Well, thank you for joining me and thank you for letting me interview you. That was great.
Okay.